Hello everyone, my name is Arya Samantha and I am a PhD student in climate sciences at the University of Tübingen in Germany. And as a climate student, my interest has been to look at the climate impacts of large-scale photovoltaics and other land surface modifications, and to characterize how the models and the observations from satellites show us about these large-scale modifications. So welcome to today's tutorial where we will try to calculate the Nino 3.4 index, which is an important index for characterizing the El Nino Southern Oscillation. Okay, so in order to first understand how to calculate this index, let's understand what is ENSO. ENSO is a oscillation of the equatorial sea surface temperatures of the tropical Pacific. Um, along the shores from the South America to the Eastern Australia. It has been seen then that in a cycle of 2 to 7 years, there is sometimes a warming of this equatorial sea surface temperature and sometimes cooling of it. Why is it important? Because not only does it change the temperature of the sea surface here, but it also changes weather patterns, most importantly, the monsoon in the East Asia and India, as well as weather systems in Northern and Southern America. So it has it has long range effects rather than just this oscillation of the sea surface temperature here. Now, in order to understand this, we study a certain box called the Nino 3.4 box, which is represented here. And it is a representation of the average sea surface temperature across the band from the South America to the Australia. So once we get our data and we crop it to the region of this, we will compute the Nino 3.4 index. So let's get right into the calculation of this index. Um, before going there, I've mentioned that just like you crop an image in your phone to show a particular area, in programming using Xarray, we can use the .where method, which is described here, with the specified latitude and longitudes, which your box encloses, to crop a certain data set. And as visualized in the next plot, you can see that your entire data set now is restricted to this particular box. This is what we want to calculate the 3.4 index. Next, we jump into calculating the anomalies. What is an anomaly? Anomaly. An anomaly is the change, is the of a particular time series from its mean. And here, first, you see that we group the entire time into monthly, because we do not want weekly disturbances. This is the long-term temporal signature we are interested in. Next, we calculate the mean and we subtract the mean away from it. Finally, we do here a weightage. Why do we do weightage? Because if we just scroll up and look at the grid boxes of this data set, the polar grid boxes are smaller than the equatorial grid boxes. Therefore, we weight according to the area of the grid box to get a much better representation of the average. Then, as per the definition, we do a rolling window of 5 months and take the mean. How do we do this? We use the dot rolling X-ray method. Great method. We just have to provide the time parameter is 5. And if you want, you can center it so that now the window is t minus 2 to t plus 5 for all the months that you have enough buffer. And then you get the index rolling mean. We plot it with the non-rolling mean to see that it's basically the same except for the spikes. Finally, in order to get how much more colder or warmer it is from usual, we divide it by the standard deviation to get a more precise estimate. Once we have done this, we can use matplotlib library functions to plot our time series of this index to now see certain years which are clearly warmer than usual. The 3.4 index defines plus or minus 0.4 degrees from usual as the La Nina and the El Nino, the El Nino and the La Nina phase. The El Nino is the warmer and the La Nina is the colder phases. So yes, thank you for your attention.